Hello, welcome to Microsoft Azure Cloud channel. In this module, we will talk about Azure Synapse in detail. What is Azure Synapse Analytics? Azure Synapse is a limitless analytics service that brings together enterprise data warehousing and big data analytics. It gives you the freedom to query data on your terms using either serverless on-demand or provisioned resources at scale. Azure Synapse brings these two worlds together with a unified experience to ingest, prepare, manage, and serve data for immediate business intelligence and machine learning needs. Azure Synapse has four components. They are Azure Synapse SQL, Spark, Data Integration, and Studio. And Azure Synapse SQL is a complete T-SQL-based analytics. So we have SQL Pool and SQL On Demand. So SQL Pool, we pay for data warehouse units provision, and SQL On Demand, it's pay for terabytes processed. The key components of big data solutions. In a cloud data solution, data is ingested into big data stores from a variety of sources. Once in a big data store, Hadoop, Spark, and machine learning algorithms prepare and train the data. When the data is ready for complex analysis, Synapse SQL Pool uses Polybase to query the big data stores. Polybase uses standard T-SQL queries to bring the data into Synapse SQL Pool tables. Synapse SQL Pool stores data in relational tables with columnar storage. This format significantly reduces the data storage cost and improves query performance. Once data is stored, you can run analytics at massive scale. Compared to traditional database systems, analysis queries finish in seconds instead of minutes or hours instead of days. Let's talk about Synapse SQL MPP architecture components. Synapse SQL leverages a scale-out architecture to distribute computational processing of data across multiple nodes. The unit of scale is an abstraction of compute power that is known as data warehouse unit. Compute is separate from storage, which enables you to scale compute independently of the data in your system. Synapse SQL uses a node-based architecture. If you look at the diagram, you can see that architecture components. The applications connect and issue T-SQL commands to a control node, which is the single point of entry for Synapse SQL. The control node runs the MPP engine, which optimizes queries for parallel processing and then passes operations to compute node to do their work in parallel. The compute nodes store all user data in Azure storage and run the parallel queries. The data movement service is a system-level internal service that moves data across the nodes as necessary to run queries in parallel and return accurate results. With decoupled storage and compute when using Synapse SQL Pool can independently size compute power irrespective of your storage needs. And it grow or shrink compute power within a SQL pool without moving data. It can pass compute capacity while leaving data intact, so you only pay for storage, and resume compute capacity during operational hours. Let's talk about Azure Storage. Synapse SQL leverages Azure Storage to keep your user data safe. Since your data is stored and managed by Azure Storage, there is a separate charge for your storage consumption. The data is shared into distributions to optimize the performance of the system. You can choose which sharding pattern to use to distribute the data when you define the table. These sharding patterns are supported as distribution, round robin, and replicate distribution. Let's talk about control node. The control node is the brain of the architecture. It is the front end that interacts with all applications and connections. The MPP engine runs on the control node to optimize and coordinate parallel queries. When you submit a T-SQL query, the control node transforms it into queries that run against each distribution in parallel. What are compute nodes? The compute nodes provide the computational power. Distributions map to compute nodes for processing. As you pay for more compute resources, distributions are remapped to available compute nodes. The number of compute nodes ranges from 1 to 60 and is determined by service level for Synapse SQL. Each compute node has a node ID that is visible in system views. We can see the compute node ID by looking for the node ID column in system views whose names begin with system.pdw_nodes. Let's talk about data movement service, that is DMS. Data movement service is the data transport technology that coordinates data movement between the compute nodes. Some queries require data movement to ensure the parallel queries return accurate results. When data movement is required, data movement service ensures the right data gets to the right location. Let's talk about distributions. A distribution is the basic unit of storage and processing for parallel queries that run on distributed data. When Synapse SQL runs a query, the work is divided into 60 smaller queries that run in parallel. Each of the 60 smaller queries run on one of the data distributions. Each compute node manages one or more of the 60 distributions. A SQL pool with maximum compute resources has one distribution per compute node. A SQL pool with minimum compute resources has all the distributions on one compute node. Let's talk about hash distributed tables. Hash distributed table can deliver the highest query performance for joins and aggregations on large tables. To sort data into a hash distributed table, a hash function is used to deterministically assign each row to one distribution. In the table definitions, one of the columns is designated as the distribution column. The hash function uses the values in the distribution column to assign each row to a distribution. If you see in the diagram, it illustrates how a full gets stored as a hash distributed table. Each row belongs to one distribution. A deterministic hash algorithm assigns each row to one distribution. The number of table rows per distribution varies as shown by the different sizes of the tables. These are performance considerations for selection of a distribution column, such as distinctness, data skew, and the types of queries that run on the system. Let's talk about round-robin distributed tables. A round-robin table is the simplest table to create and delivers fast performance when used as a staging table for loads. A round-robin distributed table distributes data evenly across the table but without any further optimization. A distribution is first chosen at random and then buffers of rows are assigned to distributions sequentially. It is quick to load data into a round-robin table, but query performance can often be better with as distributed tables. Joins on round-robin tables require reshuffling data, which takes additional time. Let's talk about third one, replicated tables. A replicated table provides the fastest query performance for small tables. A table that is replicated caches a full copy of the table on each compute node. Consequently, replicating a table removes the need to transfer data among compute nodes before a join or aggregation. Replicated tables are best utilized with small tables. Extra storage is required and there is additional overhead that is incurred when writing data, which make large tables impractical. The diagram shows next to replicated tables, a replicated table that is cached on the first distribution on each compute node. What are data warehouse units? A Synapse SQL pool represents a collection of analytic resources that are being provisioned. Analytic resources are defined as a combination of CPU, memory, and I/O. These three resources are bundled into units of compute scale called data warehouse units, DWUs. A DWU represents an abstract, normalized measure of compute resources and performance. For higher performance, you can increase the number of data warehouse units. For less performance, reduce data warehouse units. Storage and compute costs are built separately, so changing data warehouse units does not affect storage cost. Performance for data warehouse units is based on these data warehouse workload metrics. How fast a standard SQL pool query can scan a large number of rows and then perform a complex aggregation. This operation is I/O and CPU intensive. And next one, how fast the SQL pool can ingest data from Azure storage blocks or Azure data lake storage. This operation is network and CPU intensive. And next one, how fast the create table as selective SQL command can copy a table. This operation involves reading data from storage, distributing it across the nodes of the appliance, and writing to storage again. This operation is CPU, I/O, and network intensive. These are all performance for data warehouse unit is based on the data warehouse workload matrix. So choose based on these three. Let's talk about how about like increasing data warehouse units. When we increase data warehouse units, linearly changes performance of the system for scans, aggregations, and other statements, increases the number of readers and writers for poly-based load operations, increases the maximum number of concurrent queries and concurrency slots. Let's talk about performance tiers and data warehouse units. Each performance tier uses a slightly different unit of measure for their data warehouse units. This difference is replicated on the invoice as the unit of scale directly translates to billing. Generation 1 data warehouses are measured in data warehouse units, DWUs. Generation 2, Gen 2 data warehouses are measured in compute data warehouse units, CDWs. Let's choose like how many data warehouse units do we need? Let's take an example. The ideal number of data warehouse units depends very much on our workload and the amount of data we have loaded into the system. What are the steps for finding best DW for our workload? Step 1, we can begin selecting a smaller DW. And step 2, we can monitor our application performance as we test data loads into the system, observing the number of DWs selected compared to the performance we observe. And then step 3, we can identify any additional requirements for periodic periods of peak activity. Workloads that show significant peaks and through an activity may need to be scaled frequently. SQL Pool is a scale-out system that can provision vast amounts of compute and query sizable quantities of data. If we want to change data warehouse units, we can always scale up and scale down. I have one video session available in my channel. Please go through that. We can log into Azure portal and then we can scale up the DW and we can scale down. We can go to that Azure Synapse overview page and go to scale and we can make the changes. Please go through that videos module so you get more idea how to change data warehouse units. The cheat sheet shows in the diagram, it provides helpful tips and best practices for building Azure Synapse solutions. Here we can see what we should aim for. First, we need to load our data as fast as possible to a staging table. The next, limit data movement when you group by and join tables, and then optimize the table for read performance with the right indexing, and improved performance when you filter on the partition key and help manage the data lifecycle and minimize the disruption for our business users. Now I will talk about all this in detail. Let's talk about queries and operations across tables. When you know in advance the primary operations and queries to be run in your data warehouse, you can prioritize your data warehouse architecture for those operations. And these queries and operations might include joining one or two fact tables with dimension tables, filtering the combined table, and then appending the results into a data mart. And the next one, making large or small updates into the fact tables, fact cells, and appending only data to our tables. So let's talk about data migration. So we are loading data from Azure Data Lake Storage or Azure Blob Storage, and we can use a Polybase to load data into staging tables. First, we load our on-premises data into Azure Data Lake Storage or Azure Blob Storage. So the design and recommendations, the design distribution, the recommendation is round robin, and indexing is heap, and partitioning none. And then next one, distributed or replicated tables. So we have some tips from Microsoft Azure. So we start with round robin, but aspire to a hash distribution strategy to take advantage of a massively parallel architecture. And we make sure that common hash keys have the same data format, and we don't distribute on varchar format, and dimension tables with a common hash key to a fact table with frequent join operations can be hash distributed. And we can use a system.nodes partition stats to analyze any skewness in the data. And we can use system request steps table to analyze data movements behind queries. monitor the time broadcast, and shuffle operation state. And let's talk about index on the table. The Microsoft Azure provides tips. On top of a clustered index, we might want to add a non-clustered index to a column heavily used for filtering. And we have to be careful how we manage the memory on a table with CCI. When we load data, we want the user to benefit from a large resource class. We make sure to avoid trimming and creating many small compressed row groups. On Gen 2, CCI tables are cached locally on the compute nodes to maximize performance. For CCI, slow performance can happen due to poor compression on our row groups. If this occurs, rebuild and reorganize our CCI. We want at least 100K rows per compressed row groups. The ideal is 1 million rows in a row group. Let's talk about partitioning. We might partition our table when we have a large fact table, like a greater than 1 billion rows. In 99% of cases, the partition key should be based on date. With staging tables that require ELT, we can benefit from partitioning. And let's talk about incremental load. If we are going to incrementally load our data, first make sure that we allocate larger resource classes to loading our data. This is particularly important when loading into tables with clustered column indexes. The Azure recommends using Polybase and ADF version 2 for automating ETL pipelines into a data warehouse. For a large batch updates in historical data, considering using a CTAS to write the data we want to keep in a table rather than using insert, update, and delete. And let's talk about maintain statistics. Until auto statistics are generally available, manual maintenance of statistics is required. It is important to update statistics as significant changes happen to our data. This helps optimize the query plans. We can also define the frequency of the updates. For example, if we want to update date columns where new values might be added on a daily basis, we gain the most benefit by having statistics on columns involved in joins, columns used in the where clause, and columns found in group by. Best practices for Synapse SQL pool in Azure Synapse Analytics. We can always reduce cost with pass and scale. So we can pass these Synapse, like in example, on the weekends, if we don't have much workload, if we don't have any jobs running, we can pass it and then we can resume it again. So this helps reduce cost. And let's talk about group insert statements into batches. A one-time load to a small table with an insert statement or even a periodic reload of a lookup may perform well for our needs with a statement like insert into table values, just like two values. And the next one, use Polybase to load and export data quickly. SQL Pool supports loading and exporting data through several tools, including Azure Data Factory, Polybase, and BCP. For small amounts of data where performance isn't critical, any tool may be sufficient for the needs. However, when we're loading or exporting large volumes of data or fast performance is needed, Polybase is the best choice. Polybase is designed to leverage massively parallel processing architecture and will load export data magnitudes faster than any other tool. Azure Data Factory also supports poly-based loads and can achieve similar performance as CTAS. Next one, load then query external tables. While polybase, also known as external tables, can be the fastest way to load, it is not optimal for queries. Polybase tables currently only support Azure blob files and Azure Data Lake storage. These files do not have any compute resources backing them. Let's talk about hash distribute large tables. These are the best practices, and we're talking about hash distribute large tables. By default, tables are round robin distributed. This makes it easy for users to get started creating tables without having to decide how their tables should be distributed. Round robin tables may perform sufficiently for some workloads, but in most cases, selecting a distribution column will perform much better. The most common example of when a table distributed by a column will far outperform a round robin table is when two large fact tables are joined. And let's talk about do not over partition. While partitioning data can be effective for maintaining a data through partition switching or optimizing scans by with partition elimination, having too many partitions can slow down the queries. Having too many partitions can also reduce the effectiveness of cluster column store indexes if each partition has fewer than 1 million rows. So we should keep in mind that behind scenes SQL pull partitions data for us into 60 databases. So if we create a table with 100 partitions, this actually results in 6,000 partitions. And next one, minimize transaction sizes. Insert, update, and delete statements run in a transaction, and when they fail, they must be rolled back. To minimize the potential for a long rollback, minimize transaction sizes whenever possible. This can be done by dividing insert, update, and delete statements into parts. For example, if we have insert that expect to take 1 hour, a possible break up the insert into 4 parts, which will each run in 15 minutes. Leverage special minimal logging cases like CDAS, truncate, drop table, or insert to empty table to reduce rollback risk. And next one, reduce query result sizes. This step helps avoid client-side issues caused by large query result. We can edit our query to reduce the number of rows returned. Some query generation tools allows you to add top-end syntax to each query. Then next one, use the smallest possible column size. The next one, reduce query result sizes. This step we already discussed. And next one, use the smallest possible column size. When defining a DDL, using the smallest data type that will support data will improve query performance. This approach is particularly important for char and varchar columns. And next one, use temporary heap tables for transient data. When you are temporarily landing data, you may find that using a heap table will make the overall process faster. If you are loading data only to stage it before running more transformations, loading the table to heap table will be much faster than loading the data to a clustered column store table. And other two, use larger resources class to improve query performance and use smaller resource class to increase concurrency. These are all best practices for Synapse SQL pool in Azure Synapse Analytics. So far in this module, we covered Azure Synapse in detail. If you have any questions on Azure Synapse, please post it in the comments. If you like this video, please subscribe and share the channel. Thank you.